This is kind of just a fun but useful problem. I'm going to show that the work done by the gravitational force does not depend on path by giving 3 different examples. So let's talk about work. Why do we care about work? Well, work is important in the work energy principle, which says that the work is a change in energy for some system. Why is it important to look at this for gravity? Well, if you can show that the work done by force does not depend on a path, you can actually move that work done by that to the other side and call it a potential energy with the negative sign. And so that's what makes it possible that you can have the change in gravitational potential energy as mg change in y for gravity. And so we can show this. But the first thing is to show that it doesn't depend on the path. Now, just showing 3 different paths doesn't necessarily mean it's path independent, but it's a good hint. So let's imagine the following path. I'm going to go from A to C. So for this first path, I'm going to go straight down to point B, and this is 1, and this is 1, just to make things easier. So I'm going to go straight down to point B, and then straight over to point C, and I'm going to calculate that work. And then I'm going to go from here to there, along a straight line, and calculate the work. And then I'm going to go along this curved path. That's going to be fun. I guess you could go this way too. That'd be pretty fun. I might be able to do that one. Okay, so let's get to it. We define work for suppose I have some displacement delta R, and I have some force acting on it, F. Well, how do I calculate the work along that path? It's just F delta R, where this is the dot product. So if you have A as the vector AX, AY, AZ, those are 3 components of A, and B is BX, that's an X, BY, BZ. Then A dot B is the scalar, AX times BX plus AY times BY plus AZ times BZ. Now, another way to find the dot product is take the magnitude of F, the magnitude of the displacement vector, times the cosine of theta, where theta is the angle between them. Okay, so we can do it both ways. We'll just do whatever's useful. I like the dot product way just because I like dot products. But let's do this first path, path 1. I'll call it path 1. So I'll write this, path 1. A to B to C. And so let's just do this. So work equals work A to B plus work B to C. So I have 2 paths. So I need 2 works. So for the force, I'm just going to have mg, where g is the vector 0, negative 9.80 newtons per kilogram. So now I need delta R A to B. So what's the vector going from A to B? Now there's a couple ways you could do this. I don't think it's too much of a stretch to write it as the vector 0, negative 1, 0. Is that okay? Can we just do that? I mean, if I'm going from there to there, that's a vector. So now I can go ahead and do work A to B. It's going to be m times 0, negative 9.80 dot 0, negative 1, 0. So if I do the dot product, let's say that I have a mass of 1 kilogram. So it's going to be 0 times 1 times 0. So I get 1 times 0 minus 1 times 9.8 times minus 1, right? Because there's a minus in the gravitational force and there's a minus in the direction. And then plus 1 times 0 times 0. 0 times 0. So that's 0, and I get positive 9.8 plus 9.8 joules. So in this case, the work done by gravity is positive because the force and the displacement are in the same direction. That's what you would expect. Okay, now let's do from B to C. So work B to C, I need to know delta R B to C. That's going to be the vector 1, 0, 0. right? Because if I'm going from here to there, I'm moving 1 in the x direction. Now, if I do the dot product with this, I can get 1 times 0, 0 times 9.8, and 0 times 0. So that's going to give me 0. So the work done on BC is 0 joules, and the total work is going to be 9.8 joules. Now, we could do this the other way. I could say work A to B is mg times the displacement of 1 meter times cosine of 0. Right, so in this case, this is the magnitude of the gravitational force. That's a scalar value that's positive 9.8. That's the magnitude of the displacement. And this is the angle between them. So since they're both going down, both g and delta r down, then theta would be 0. The cosine of 0 is 1. So this gives 1 times 9.8 times 1. And then WBC is going to be equal to mg times 1 times cosine of 90, or pi over 2. Because in this case, delta r is that way, f is that way. They're perpendicular to each other. The angle between them is 90 degrees. And the cosine of 90 is 0. So either way, I get the work is equal to 9.8 joules. Okay, now let's do path 2. Get a new piece of paper. It's stuck. Okay. Path 2. Here's my diagram going from A to C. So this is, let's just say this is the vector 1, 0, 0, and this is the vector 0, 1, 0 for that one right there. And I want to go like that. So we could find this angle here. It's actually pretty easy that if this is 1 and that's 1, then this angle is 45 degrees. And I'll do it both ways. But I can also get delta r. Delta r is going to be my final position, which is 1, 0, 0, minus my initial position of 0, 1, 0. Delta r is change in position. Final position, initial position. So if I do this product, I get 1 minus 0 is 1. 0 minus 1 is negative 1. 0 minus 0 is 0. And so that makes sense, right? I'm going down 1 over 1. So, or over 1 and down 1. And that vector does agree with what I'd expect right there. So that's my displacement. Now I can do work. It's going to be equal to, I'm going to multiply the 1 inside. So I have the force is 0, negative 9.8 newtons, 0, dot, 1, negative 1, 0. So now if I do the dot product, I get 0 times 1 is 0 times 1. Negative 9.8 times 1 is going to be, I'll just write that as plus negative 9.8 times negative 1 plus 0 times 0. So 0 times 1 is 0. Negative 9.8 times negative 1 is 9.8, 0. Same thing. Okay, so now let's do it the other way. If that's my gravitational force and that's delta r, then the angle between them is theta. Okay, but now I have to deal with this total distance. So if I do work is f delta r cosine theta, well, f is mg. Delta r is going to be the hypotenuse of this. So it's actually going to be equal to the square root of 1 squared plus 1 squared plus 0 squared, right? It's going 1 in the x direction, 1 in the y direction, 0 in the z direction. So this is the square root of 2. So work is going to be mg, which is 1 times 9.8, and these are positive numbers, right? Because I'm using the magnitude. Delta r is going to be the square root of 2, cosine of 45. So the cosine of 45 is, yes, it's 1 over the square root of 2. If you want to put that in your calculator and you don't trust me, that's fine, but you can. So I get 9.8 joules. Okay, so work path 1, work path 2, the same thing. Work path 3 is tricky. Now, there is a way to do this with calculus, but we're not going to do that. So let's start right here. Here's point A, here's point C, and this is a circle. Oh, missed it. Okay. So we have a problem here because, yes, the gravitational force at this point is down. And the displacement is right that way. But up here, the displacement's that way. So the displacement keeps changing directions the whole time it's moving. So I can't do work equals F dot delta R. That is only true if F and delta R are constant vectors. But here, even though the force is a constant value, the displacement vector delta R changes in direction. So we have a problem. Now you could set up an integral to do this, but we're going to do it in Python instead. So we're going to do the following. I'm going to do this. So here's A. I'm going to draw it like this. And there's C. So what if I just broke this into steps? Like this. This is a very few steps. Okay. So if I break this going into this piece, then I have delta R as that. And I can approximate delta R as constant along that path. And I can calculate just a little bit of work along that path. I'll call it dW. So in that case, dW is F dot dr. Now I can move my position to right here and have a new dr going this way. Now, if I assume delta R is constant over this path, I can calculate another work. And then I can add it to the total. And then I can calculate the work along this path and this path. So I can break it into a whole bunch of short paths that are approximately constant. And so, of course, we could do this on paper, but it'd be easier to do it in Python. So here's what we're going to do. I'm going to start with this vector R as the location of my object with some angle theta. And I can then say d theta is 0.1 radians and just keep increasing theta until I get down to here. So a lot of times we measure theta from the x-axis. I'm going to start up here where theta is 0 just because I like it that way. So I'm going to go from theta equals 0 to theta equals pi over 2. And then all I need to do is to calculate the vector direction, dr, for each one of those paths. So if I have a step size of delta theta at the step angle, I can calculate the length of this right here. I can say S is R delta theta, right? Because that's the arc length of that piece. But I actually need delta R as a vector. So here's a tiny little trick. So I'm going to say delta R. You could do it manually if you wanted to. It's going to be S, the length, times R hat cross Z hat. I know that's a lot. But, so the cross product gives you the direction of a resultant vector. Z hat has a magnitude of 1. R hat has a magnitude of 1, because I'm making it that way. Then I multiply it by my unit vector ds. And in fact, I could just say dr is going to be equal to, I can bring that r in. I can say delta theta r cross z, even though r is 1, so it doesn't really matter. No, z hat. So the right-hand rule says that if I have r right here, r cross z has to be perpendicular to r and z. So z is coming out of the paper like this. So r cross z would, using the right-hand rule, come up this way and be in the right direction. So now we have a vector for that. And as we change theta, we change r, we can find new delta r. It might make more sense when we put it in Python, and so we can visualize it. But hopefully at the end, we should get a work done by adding up all the works at something close to 9.8. It won't be exact because we're making an approximation. Okay, so let's jump over here to Python. Okay, so I'm in GlowScript v Python, and I will give you this code. Let's just start off with some stuff. G equals vector 0, negative 9.8. 0 and mass equals 1. Okay. Now, the first thing I just want to do is to make a ball. I'm going to make a visual ball and have it move along that angle. So I'm going to say theta equals 0, d theta equals 0.1. We can change these things later if we don't like it. And I'm going to calculate the vector r, right? I'm going to say r is going to be equal to 1. Let's just say this. r equals 1. That's the length, the radius of the circle. R is the vector, r times vector. One of the nice things I like about GlowScript VPython is that it has vectors built in. Boom. Okay. So it's going to be the vector sine theta, cosine theta, 0. And like I said, sine is in the x direction because I'm measuring the angle from the y direction. So if you look at the picture, that shouldn't be too difficult. Now let's put a ball there. Ball is an object of type sphere. Its position is r. Its radius is, let's say, 0.05. And let's do this. Make trail equals true. Okay, so all I want to do is move that ball along that path. I'm not going to calculate work. I'm just moving the ball. So let's say while theta is less than pi over 2, I'm going to give it a rate of 10. This just says don't do more than 10 calculations per second, so we can see it moving. You don't have to have that in there, but I like it. Okay, so the first thing we're going to do is to put the ball at the position of theta. So I'm going to say, even though I've already done this, I'm going to say ball.pos equals, let's calculate r. I'm just going to recalculate r up here. And you may get into these programming order problems, but the order of calculations can always be fixed by having smaller step sizes, so it's not a big deal. Okay, so then the ball position is going to be r. And then I'm going to increase theta. Theta equals theta plus d theta. And then that's it. It should move in a quarter of a circle. Think. There we go. Nice. Very nice. Okay. So let's go back over here. Let's save it. Work done by gravity circle. I don't know. I'll give you the code. Don't worry about that. You're going to get the code. Okay, so it's moving along the path. What I want to do now is to draw an arrow representing dr. Or I'll call it dl, just so that we can visualize that. So let's say dl, I'm going to actually make it an arrow, equals an arrow. Its position is going to be the ball, and its axis is going to, so when we make an arrow in VPython, we have two important properties. One is the position, the location of where that arrow starts, and the other is the actual length of the arrow. So this is going to be equal to d theta, just like I said, times the cross product of r and the vector z, which is going to be vector 0, 0, 1. I think that will work. Okay, and should I make it yellow? Let's make it yellow. Color equals color dot yellow. I think that should work. Okay, so now down here, after I move the ball, I need to move the arrow. So I'm going to say dl.pos equals ball.pos, and then I need to change the direction. So dl.axis equals, I'm just going to do the same thing I had up before, d theta times cross, not course, no, cross, r vector 0, 0, 1. And so r changes, so that cross product changes, so it should change. Let's see what happens. Okay, it is yellow. Okay, it's just a little small, and that's fine. Let's just make it bigger just for effect. Okay, it's the actual size of the step. That's why it's so small. So let's just say SC for the scale. I'm just going to make it twice as big. So down here, I'm just going to put in SC. I'm going to put in SC. Okay, now let's see what it looks like. Nice. It's going in the right direction. Everything seems to be fine. So now I can calculate the work. So up here, I'm going to say work equals 0. Because remember, I'm going to calculate the work along each little piece. I'll call that dw. And then I need to add it to this. So I need to start it at something. I'm going to start it at 0. So let's just do, there's my r. Let's go ahead and calculate the work. dw equals, let's just say m times g. That's the force. Oh, no, I'm sorry. Dot m times g dl. dl dot axis. So dl is an object of an arrow. The actual okay, I'm going to take off this. So it's going to be wrong because I have that SC as 2. So that would make it twice as much work because I'm doing the actual length. So I'm switching the arrow back to its real length. It's the real length. Okay. So that's the work done along that path. The dot product's a built-in function into GlowScript v Python, just like the cross product is, which is really kind of nice. So now I just say work equals work plus dw, and that should be it. I do need to print that. Print work equals w joules. 8.6. Okay, so it's not that. It's not the right answer. But if I take my d theta and make it 10 times smaller and run this 10 times as fast, I have a lot smaller steps. You can't even see the arrow, it's so small. And I get 9.7. So it's still a little small, but again, it's approximation. So we can fix that. Let's just go even smaller. I'll just do half as small and run this 10 times as fast. Okay, so I think it's pretty good. I'm pretty happy. Now, I did say one thing, right? What if I want to go from here and go around the other way? Could I do that? Well, I think I can. So if I have theta as that, everything's the same, but what if I do this? Theta equals theta minus d theta. So then it's going to go negative until it will eventually get and as long as theta is greater than that'd be pi, is it 3/4? No, 2 pi. So while theta is less than, no, minus moves the other way. I don't think I want to do that. I want to do, let's do this as plus. Let's just imagine theta is going the other way. Then my x component is going to be negative sign. So I think I can just come up here and say r is going to just have negative sign, and this is negative sign. And I want to go until 3/4 of 2 pi. So it's 3/4 of 2 pi. So 3/2 pi. So while it's less than 3/2 pi. I think this may work. I don't know. And I think I have the dr wrong. But let's just run it. Okay, so it did it. And all I need to do is change this. Right now my dr is going the opposite direction. So I can just say negative 1 up here. And that'll be fine. -1. 9.8. Boom! I'm pretty happy with that. So that was actually 4 paths, even though I said I was only going to do 3. 3 paths, work is the same. So now you can use, well, plausibly at least, you can use the work done by gravity and move it over as a potential energy, which is pretty nice. You don't have to worry about the path, then you can just use the change in potential. Okay, that's that.